In this video, I'm going to review the free response section of the June 2018 Regents Chemistry exam. The free response section sometimes is daunting and sometimes scary for some students because they have to generate the answers. But hopefully through this video, you can see that all you have to do is use the same concepts that you use in the multiple choice, okay, in this section. Okay, some people actually find it easier once they get over the hump of the daunting idea of trying to come up with an answer without multiple choice selections. So let's be crazy and start in order with the first one, number 51. Number 51, state the general trend in the first ionization energy as elements in period 3 are considered left to right. Okay, so what is this general trend? General trend, this is periodic properties, and there are some trends, okay? So we're looking for the first ionization energy in period 3, going left to right. So what we're talking about is this ionization energy. Now, ionization energy is one of those types of values that we measure that gives us an idea whether something is a metal or a non-metal. So ionization energy is the energy needed to pull an electron from an atom. Okay, so if we have an atom, and every time you say atom, I say neutral. Atom, neutral. Okay, atoms are always neutral. The protons equal the electrons. Now, basically, we give it energy, okay, and with that energy, what we get is something that is an ion that of course is positively charged, and of course an electron comes off. So it's the energy needed to pull an electron. So it's a value that we can look to see how well atoms hold on to electrons. Now we're talking about period 3, and it won't matter what period. Period, of course, is the row on a periodic table. That's important. So we're going from left to right on the row. And if we're going from left to right, okay, what happens? Let's go to the periodic table. Before we do so, we should know something going left to right. We know that the periodic table increases in atomic number as we go across. So as I add my atomic number, okay, the actual pulling force of the nucleus increases, and the electrons are held more strongly as I add more protons, right? So we would expect to take more energy, okay? It would take more energy to pull that electron away. And you should know that non-metals exist all the way to the right of the periodic table because they have the greatest attraction for electrons. That's called electronegativity, which means because they have the greatest number of protons in their row, it'll take the greatest energy to remove them. Non-metals have higher ionization energies. And we should know that to the left of the periodic table, mostly, we have mostly metals. And they hold on to electrons loosely because they have less protons in their energy level. Okay, which means electrons are held more loosely and easier to remove. Hey, metals lose electrons, non-metals gain. It should make sense that if non-metals are good at gaining electrons, they what? Need more energy to what? Give them, to separate them. Metals are loosely held. So let's go to the periodic table for a second. So as we look at the periodic table, we can see that we have these periods here. Okay, the period is here, so period 3, it won't matter. And here is the what? The atomic number. The big number here is the number of protons. And of course, it's increasing as we go left to right. So the number of protons are increasing. So we'd expect having more protons in my nucleus, the electrons are going to feel the nucleus more and be harder to remove, thus need more energy. So the trend, you should understand, is that the ionization energy, the energy needed to remove an electron, has to increase if there are more protons attracting them. But if you don't know that, the most underutilized table is table S that lists ionization energies. Let's go there for sodium through argon. Table S, very underutilized table. I have fluorine highlighted for some reason, but here's my first ionization energy. Don't worry about the word first. It just means the energy to remove the first electron. You only deal with first ionization energy or just ionization energy. But remember, we are dealing with atomic number 11, okay, all the way through, okay, to argon. This 11 through 18 is period 3. It wouldn't matter what row we're working on, the trend is the same. And what happens to the ionization energy? Notice it steadily what? Increases as we go from sodium all the way down to argon. Why does it increase? Because the number of protons are increases. Sodium has 11, argon has 18, so clearly you could have read that right from table S. All right, so it's back to the answer booklet. Let's get that down. So I wrote the first ionization energies increase from left to right in period 3. I mean, so many ways to say it. You could have just said the first ionization energies increase, since the question was asking what happens from left to right. But bottom line is that the trend is that there's an increase in energy needed to remove an electron. Okay, so moving on to number 52. Number 52, identify the type of strong intermolecular force. Okay, that's important that you understand what that is. Strong intermolecular force. Sometimes we like to call them IMFs. Okay, that exist between water molecules but not carbon dioxide molecules. So an intermolecular force is a force between molecules. Molecules have bonds in them, okay, but have attractive forces between them. It is these attractive forces that decide whether the compound is a solid, liquid, or a gas. Solids have stronger, liquids have weaker, and a gas, which has tremendous energy, can fly around the room hundreds of miles an hour, have even weaker. And if it's an ideal gas, they have no attractive forces. So in order to know what these attractive forces are, we have to know what type of molecules these are, because if they're polar or nonpolar, they'll exhibit different type of attractive forces. So you have to know that water, okay, is a polar molecule. If you do the Lewis dot diagram, oxygen has 6 valence electrons, and each hydrogen has 1. And so you get this Lewis dot diagram. It's a bent molecule. And one way, an easy way to know if the molecule is polar or not, you look at its symmetry. Since there's not H's all the way around, the way we love to draw water with this dash, which is an electron pair, is like this. And so water does not have H's in all 4 directions, so it is asymmetrical. There's an asymmetrical distribution of charge, which means there's more electrons over here, and that's the negative side. And this is the positive side, okay? So what type of attractive force exists between water molecules? Well, if we draw the actual molecule of water like this, how does it attract another water molecule? Well, another water molecule looks the same way, and you should have drawn water a million times in your course, maybe 1,000,001, and you should recognize that the negative side, okay, of this molecule is the side that has the oxygen because it's more electronegative. See, this oxygen pulls electrons toward the oxygen. That's why these bonds are polar. So this is an electron-rich area. This is an electron-rich area. This is an electron-poor area. If the oxygen is pulling electrons, this is the positive area. And this positive area attracts the other negative area. So the attractive force that happens between water, it's a misleading term because it's an intermolecular forces attraction, but someone somehow thought it'd be a great idea to call it H bonding, and it's called H bonding. So the type of attractive force that we have between is called H bonding. It's not a bond, but it's a very strong attractive force, okay, between the positive H end, which is an electron deficient H that attracts the negative end of the oxygen. And it's so strong, okay, water is pretty light. It's 18 grams per mole, yet it exists, okay, as a liquid at room temperature. Why? Because of the strong attractive forces. It really, really resists boiling. This liquid doesn't easily evaporate. You know this because puddles will stay around for a long time after a rain. And to boil water, it takes tremendous amount of heat. We see that when we boil water when we cook. Now CO2, I'll draw over here. CO2, carbon has 1, 2, 3, 4 valence electrons. Oxygen has 6, 1, 2, 3, 4, 5, and 6. And I drew it this way because oxygen has 6 valence electrons, and I can draw that in red to make some sense here. All right, so here's the red electrons that belonged to oxygen originally. And now by sharing, okay, we can see that oxygen feels like it has 8, it fills its octet. And so another oxygen on the other side does the same thing. It has its 6 valence. It donates kind of 2 to that bond. And for the same reasoning, it's sharing 8, and they are forced to share because these are nonmetals with high attraction, so they can't transfer. And of course, the carbon, by having a double bond with the oxygen, feels like it has 8. So what we have here is a carbon double bonded to an O. And this is another Lewis dot diagram that you should have drawn a million times. It's one that pops up all the time on this test. So if you don't like Lewis dot diagrams, hey, memorize the structure, okay? But what you should know is CO2, because it is symmetrical, there's a symmetrical distribution of charge. This side of the molecule has the same amount of electrons as this side. So there's no difference. Therefore, there's no poles. What does polar mean? Polar means differences. Hey, water has differences. There's electron-rich area and electron-poor area. This doesn't. So this is, while this side was a polar molecule that had H's attracted to a very electronegative atom, which gives it H-bond attractions, this is a nonpolar molecule. And this nonpolar molecule sticks together by something called, in this course, weak forces. There's an actual name for it, but we'll call it weak forces in this course. And why they're weak? Because there's no true positive or negative. We'll just keep it at that. Now, so that's what we're doing. So water has H bonding. Okay, now so let's look at the question again. Identify the type of strong intermolecular force that exists between water molecules but does not exist between carbon dioxide. They don't say why. So H bonding exists between water, but it does not exist between carbon dioxide. And knowing why helps you come up with the answer because this is non-polar. So let's get this down into the answer booklet. So 52 is H bonding. Now, also, because water is polar, okay, you could have also say dipolar forces. And what does that mean, dipolar forces? Hey, positives attracting negatives. So you could put also dipolar forces, okay? Because again, water is polar. So you definitely could have used and put that instead. But when it comes to water, just remember H bonding, that's a key word that comes up. All right, so on to 53. Okay, number 53, draw a structural formula for 2-butanol. Remember, you're gonna have to put this in your answer booklet. Now, it's important that you know that structure is king. The naming system, the IUPAC naming system that we use for organic molecules is based on the structure, because if you change the structure, you change the chemical and physical properties. Structure is king. That's an important point that comes up in the multiple choice questions. And again, the questions that we have done already, whether it's any question, 51 through 53, all of these kind of questions could be set up as a multiple choice question. I've seen them before. You know, this could be a multiple choice question that says which of the following is 2-butanol. Okay, so we need to draw the structure of 2-butanol. And so we can use our reference tables P, okay, Q, and R. Okay, if we're from New England, we say R, R, okay, and we can get this structure. Okay, so first I look at the bute. The bute is the longest continuous chain of carbons. Hey, it's an organic molecule, it's carbon-based. How many carbons are stuck together? The next part I look at is the ane and the OL. So the bute is from the table P. The ane part, which just tells me is a single bond between the carbons, is from Q. And the OL, okay, that part comes from R. So we don't have to know this. So let's go find the bute from table P. So in table P, we have the bute, and that's 4 carbons. That would be the longest continuous chain. Okay, now the other part is the ane, the butane. Now you say A-N-E. So the A-N-E ending speaks to a saturated type of bonds, which is single bonds. You may say, well, I don't see the E. They take the E away, so it sounds nice. So to know what kind of bonds exist between them, we have to go to table Q. Let's go there. And table Q is what? A little lower than table P, so it's in the organic area. The reason why it's organic is we have carbon-based compounds. It's all about carbon. So we're going to go down to table Q, and table Q talks about the types of bonds that exist between the carbons. And we should know that these guys right here are unsaturated. They hold a maximum amount, and they're anes. Carbon makes 4 bonds, so if there's a single bond between the carbon, hey, it's more saturated. So these are the saturated ones. These are the unsaturated, under the max. Bottom line here is that because we have the ane or the an part in butane, we know that there's single bonds between the carbons. All right, back to the test again. And now we have the OL ending. That tells us the type of functional group or structure that's on the what? The organic compound. Structure is king. This defines its properties, right? So let's go find the OL ending, the type of structures that exist on carbon-based products, and that's the functional group table, table R. So we're looking for the OL ending, and there it is. It's an alcohol. This is not a base. This is covalently bonded. The hydroxide does not come off, but notice the general formula. Some people have difficult time with this. The R is the rest of the organic compound. There is the R part. And the OH is that functional group right there. And so we have, all right, if it ends in OL, it's an alcohol that has an OH group attached to some carbons. Notice the example they gave us, 1-propanol. Prop from table P means 3 carbons. Now we had a but that means 4. Ane is single bonds, and then the OL is on the first carbon. So in our case, all right, we have 2 butanol. We have 4 carbons. There's single bonds because we have an ane, and we have this OH, okay, on a certain carbon. Let's go back to the answer. Go back to the test for a second. So we have but, which is what? 4 carbons. The ane from table Q means that they're saturated bonds, single bonds. And the name 2 means on the second carbon, we're going to have this OL group, in table R is an OH. You could put that, okay, above or below the second carbon, and you could also make the second carbon be over here too, because you can flip it over. Bottom line is carbon must make 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. These dashes, and this is one dash right here, represent the H's. Again, I could put this hydroxide and put it on this side. I could also put it here on this carbon or that carbon, because if you count, okay, the way that I count, this is the first carbon, the second carbon, the third carbon, the fourth carbon. I could clearly count the opposite way. If I take this and flip it over, this OH would be on this side. So you could have clearly put the OH on any one of these internal carbons, okay, to be correct. But you needed to make sure that every carbon has the right number of dashes. These dashes represent hydrogens. You don't have to draw them. Okay, so 1, 2. So let's put this on the answer booklet because it won't count, okay, right here. So here's my correct drawing. Again, if I was missing one of these dashes, I have to have 3 H's. If there's a 1 bond here, this carbon needs to have 1, 2, 3 more to satisfy its octet. This carbon only has room for 1 H because it's bonding to what? This other carbon, 1, 2, and it's bonding to this oxygen, 3, so it only has 1 left for this H. If you're missing any of these dashes, it'll be wrong, okay? So that is the structural formula. Now, you don't have to write the H's. The dashes represent these H's here, okay? And as I said before, this OH can be on this side. It could be here or here. All right, so there is your naming system that describes the structure. On to number 54. Now, the next little question has this little table here, and it has questions. What I tell my students is, and a lot of students who go through the free response and sometimes find it to be difficult, they wind up looking at this stuff first and sometimes getting intimidated by the types of formulas and things that they write even before they get to the questions. My personal belief is for you to read the question, because so many times these questions, okay, really have very little to do with how this information is presented. They're going to ask a question that's based on the same concepts as the multiple choice, but they're pulling it out of this scenario. So don't get crazy about looking at the data and say, I'm not sure if I understand all of this. Oh, these compounds, I've never seen these before. Who cares? Go right to the question. You'll see what they're asking for. And if you have to go back, do that. That's my suggestion. It really helps a lot of students. So go to the question first. Forget about the blurb or the data here until you need it. So here you go, number 54. In terms of element classification, okay, why is silver chloride an ionic compound? Well, we could clearly have this question in multiple choice. They could say which of the following is an ionic compound, and they'll have silver chloride possibly as a choice. So this is clearly the things you've learned. You must know what things are ionic compound. Another choice could be a molecular compound or a metallic. These, of course, have different types of bonds. Molecular is covalent, metallic has metal bonds, and these, of course, have ionic bonds. So we're looking for something. Why is it an ionic compound? Okay, why are things ionic compounds? Well, what's in the word ionic? Hey, the word ion. And what is an ion? An ion is a charged atom. It's an atom that has a positive or negative charge because it lost or gained electrons. And how did that happen? How did something like sodium become Na plus? Because in this case, it lost electrons. How did something like chlorine go from an atom to Cl negative? Hey, it gained electrons. Electrons are transferred in order for atoms to become ions. And once they become charged, they stick together by their differences in charge. Hey, opposites attract. So an ionic bond is a bond between ions of opposite charges, and they stick together. So we may write NaCl, but that to me is a lie. What it really is an Na plus ion attracting a Cl negative ion, and in fact, this never occurs in one-to-one. It makes a larger crystal. This is just an empirical formula of the entire crystal. And let me write it because you need to understand things that are ionic do not make molecules. They're not NaCl. It really is an Na plus doing what? Attracting another Cl negative ion, which is attracting another Na plus ion, and the beat goes on in all directions because it makes a crystal structure, and this crystal structure is the reason why it has, okay, large melting points. All of this stuff you need to understand. But so why is it an ionic compound? Okay, for all the reasons I talked about. Let's get that on paper and pick one. All right, so I wrote ionic compounds are made from a metal and a nonmetal because of a transfer of electrons. You could say so many different things. The reaction between a metal and a nonmetal can produce an ionic compound. There was a transfer of electrons, as I said. Okay, it's ions of positive and negative attracting each other. So there's many responses to understand this, but I want you to remember transfer electrons had to occur. I would love for you to say, hey, you got positive ions, which are metals, attracting negative ions, which are nonmetals. And you should know that the metals are positive because they lose electrons, and the nonmetals become negative because they're gaining. That's really important, that electrons are transferred. And in other parts of the course, we talk about the metals losing as oxidation and gaining electron as reduction. Okay, you need to see this course as a whole, not just separate bunch of questions. All right, so the metal oxidizes where the nonmetal reduces, and that's your transfer. There's your redox reaction. And so easy way to identify an ionic compound is a metal and nonmetal, because the metal will lose and the nonmetal will gain, and you'll make ions, and they'll stick together by ions. That's ionic bonding. All right, so this is an ionic bond. So many ways to describe it. Most people just say, hey, it's a metal and a non-metal bond is ionic. I need you to understand why for other reasons and for other questions. On to number 55. Okay, number 55. This is a classic Regents chemistry mathematic problem that's on many tests. But they just want the numerical setup for calculating the percent composition by mass, okay, of silver in silver carbonate. So they're after the percent by mass of this. And they were very nice because they gave us the gram formula mass, which is the grams per 1 mole. If they didn't give us this, we'd have to count up each number of atoms using the atomic mass to get this. Now, what is a percent composition by mass? Well, there's something you could do if you forgot what this is. Table T can help you a little bit. Let's go there. So in table T, where you have your bunch of your formulas, okay, we can see that we have percent composition. And notice it's part over a whole times 100. So we need the mass of the whole and the mass of the part. And that's what we're going to use to just set up this question in our answer booklet. Let's go back to the test and set it up. So from reference table T, I know it's part over whole times 100. Now what part are they asking for? They want the mass of the silver. That's the part they're after in silver carbonate. So in silver carbonate, I've got what? 2. Look at that number. 2 silvers. Now, what's our total? What's our whole? Well, let's pick 1 mole. What's the mass per 1 mole? Hey, it's this formula mass if we add everything up. So this is going to be 276. They gave us the mass per 1 mole in the gram formula mass. Okay, again, if we didn't have that, we have to add everything up. Now, what part am I asking for? We're asking for the silvers in the silver carbonate. Okay, now there's 2 of them. So in 1 mole of silver carbonate, there's 2 moles of silver. So I have 2 times the what? Atomic mass per 1 mole of silver. So let's go find the atomic mass of silver in our reference table, because silver, Ag, okay, is going to have an atomic mass, and that mass is equal to 1 mole. It's because in the mole theory we made 1 mole of silver equal to its atomic mass. And because there's little 2 here, it's 2 of them. So let's go find that. Okay, so in silver we find it here. It's a metal, and we find that its mass is 107.868. So I can round that to 108, which is the most common isotope. So 108 grams per every mole. Okay, and we're going to times that by 2 to know that part of silver carbonate. Let's go back to the test. So this is 108. So 2 times 108 is 216, and that's our part. And that's why we put that follow right there. 216. Over that times 100. And again, remember the question. Show a numerical setup. They didn't even want the answer. So 216 over 276, the total, times 100, and that's all you need. Let's put that down in our answer booklet. And there we go. 216 over 276 times 100. Certainly, you could write it a couple of different ways. It's the same thing. You could put 2 times 108, okay, times 100, right? All over 276. Numerically, it's the same thing. You didn't have to solve for it, just the setup, okay? All right, on to 56. Number 56, identify the silver compound. Hey, they're all silver compounds in the table. Hey, here's a table that is the most soluble in water. How in the world would you know that off the top of your head? Unless you are someone who loves to memorize solubilities. I doubt that you are. Okay, so we need to find a place that tells us something about solubilities, and that, my friend, is table F. Sometimes I call it table foo-foo. Let's go to table F to see which silver compound. Okay, keep this open, and we go to table F to see which one. Silver carbonate, silver chlorate, silver chloride, or silver sulfate is the most soluble based on that table. It's a table question. Let's go. So let's go and see which one is the most soluble. Now in this table, you either have soluble or insoluble. Let's start with silver carbonate. Carbonates are normally insoluble. There are some exceptions, which means if silver is listed here, it would be soluble. But if you notice, silver is not an exception. So silver carbonate is insoluble. So that's not what we need. We want the most soluble. Okay, silver sulfate. Sulfates are normally soluble. There are some exceptions, and silver is an exception, which means when you have silver sulfate, it will be insoluble. It's normally soluble sulfates. The exception means that it's not going to be soluble if you have these guys. And silver is the exception for silver sulfate to be soluble, so it's insoluble. Hey, silver chloride is a halide. It's from the halogen family, group 17. Chlorides are normally soluble, right? But there's an exception, and silver is an exception, so therefore silver chloride is insoluble. They're normally soluble, but the exceptions will be insoluble. So that leaves chlorates. And look at chlorates, it has no exceptions, which means that silver with a chlorate will still be soluble. Silver is not listed as an exception. Silver chlorate is the most soluble. Okay, so let's put this down into the answer booklet. So I have 56 silver chloride based on table F, and I could write the chemical formula as well. Okay, on to 57. So number 57, complete the nuclear equation. This is not a chemical reaction by writing the notation for the missing particle. Now, if you notice, we have a little blurb here. I always tell my students to go right to the question. Don't let this blurb intimidate you because you don't know how and when, if you need any of that information. And for 57, you don't need any of it. Okay, all you know is if it's a nuclear equation, you know it's a nuclear equation where you have to add up all the numbers on one side equal all the numbers of the other. Okay, so this could be a multiple choice question in which they give you the nuclear equation, which I've seen, and say, hey, what is X? What's the missing particle? So let's go to the booklet. None of this is needed, and let's go answer for that notation and fill it in. All right, so 57, I have cobalt 59. Okay, I always say the number of the mass because there's different isotopes. Okay, notice it's becoming cobalt 60. Okay, so the question is, what kind of particle is missing here? Now the thing is, on a nuclear equation, we're showing how the nucleus changes, the protons and neutrons, okay, by the types of particles that are either emitted or absorbed if it's artificial transmutation. So all you got to do is see that this is 59 plus some number that equals 60. So if I write it this way, 59, which is from the cobalt, plus what? I can put the plus right alongside it. Plus, undo that too. 59 plus what number here equals 60? Tough math, isn't it? Okay, I think that's a 1. And the bottom number, 27, plus some number equals 27. Get your calculator ready. Yeah, that have to be a 0. So this is cobalt 27. This is still cobalt 27 because it's the proton number didn't change. So what particle, okay, has a 1 above it and a 0 on the bottom? And if you look at table O, that's an N. Okay, now how do I know? Go to table O. Here's table O in all of its glory. Remember, table O, okay? And then we got the neutron, 0 on the bottom to show it has no charge, and the mass of 1. And that's the particle that you needed for the point. Let's make sure we've got this down in our answer booklet. So I write 1 N and a 0. All the numbers on top on one side have to equal all the numbers on top of the other. All the numbers on the bottom of one side have to equal all the numbers. Okay, now just so you understand, there is no true conservation of mass in nuclear equations. There's a little tiny missing mass in these types of equations. Okay, so just be careful about that. All right, on to 58. So number 58 is based on this blurb, but again, oftentimes don't read it. Just go right to the question. You probably don't need it. Look at the question. Based on table N, they're telling you to go there. Identify the decay mode of cobalt-60. Hello, this is just a reference table question. So go to table N and figure out what kind of particle is given off by cobalt-60 because it's an unstable nucleus if it's radioactive. Let's just go there. It has nothing to do with this data. Don't be intimidated by the blurb. Don't let the blurb get you down. So go to table N, cobalt-60. And in table N, what do we have here? Cobalt-60, and the decay mode is this B negative, which you could write. But if you want to know what this is, if you don't know, you go to table O. So B negative, let's go find what that is. You could write that down, it would be acceptable, but let's go find what it is. Table O is your helpful friend here. And your B negative symbol is a beta particle, which you know is basically an electron. Okay, so that comes out of the nucleus to make the unstable radioactive cobalt-60 more stable, to help its proton to neutron ratio. Onto the booklet. So 58's beta particle, you certainly, as I said before, could have just wrote down the B negative symbol. Okay, if you just put a B down, that would not be right because there's a B plus symbol called a positron. You could have said just beta, beta decay. You could have put down the particle from table O. Okay, so anything that is reference to the beta particle would be acceptable. Just one of these is all you need. So under number 59. Number 59, determine the mass of the original sample of cobalt-60 produced. So this is a half-life problem. And we need some information, and the blurb finally gives us something that we need. So they want the mass of the original of cobalt-60 produced. We've got to go into the blurb. The blurb says when a cobalt-59 atom is bombarded by a subatomic particle, we found what that particle was. Okay, on 57, that was a neutron. A radioactive cobalt-60 is produced. Well, it has too many neutrons. The neutron, the proton ratio has been changed. The nucleus is unstable, which means it's going to do something. After a certain amount of years, this is how much of the original cobalt-60 remains, which means what? Some amount of it, okay, originally there's more of it, but a lot of it became something else, okay, it decayed into something more stable. So they're giving you what is left, okay? So 1.2 grams of the original sample is left, is unchanged. What's the original sample? So when we do half-life problems, I suggest you do it this way. There's so many different ways, and some people can see it. I like to start with a zero line. In this zero line, I have zero time, because at some zero time, the cobalt-60 has not decayed at all yet. So that's the original sample. Okay, wherever it might be. This is 100% of the sample. Sometimes you put 1/1 here, and we're looking for that. And there's zero half-lives that have occurred. Now, what do I know? I know that after some time period, there was 21.084 years that have transpired. And after that time period, okay, there was 1.20 grams remaining of the cobalt-60. How much of the original sample when there was zero times? Well, what happens over times is there's half-lives have occurred. We've got to figure out how many half-lives have occurred, okay? So we know the total time, but what's the half-life period, okay? And so they don't tell us this, so we've got to go somewhere that tells us for cobalt-60. And so we're going to go to table N. Table N not only gives us decay modes, it gives us the half-life time, the amount of time it takes for half of the sample. And these are always about multiple halvings. So let's go there. So cobalt-60, we already figured this out from another question that the decay mode is B negative, but the half-life time is 5.271. Okay, that's the amount of time it takes for the original sample to halve. So if you had 100 grams, now you have 50. So if we know the total time that's transpired, and we know the amount of time for it to halve, we can figure out how many half-lives have occurred. So 5.271, let's go back to the problem with that piece of information. So my half-life time is 5.721 years. That's the amount of time it takes for it to halve. And since there's 21.084 years of total time, how many halvings have occurred? So I'm going to divide by that. And when we put that in your handy dandy calculator, you'll get 4. So that means 4 halvings have occurred. So let's do that. Here's the first, second, third, and on the 4th halving, we were left with 1.2 grams. Now we have from the original sample going down, because this is going to be a smaller value because we keep halving. So this has to go backwards and double, okay, up. So what's double of 1.2? So we have 2.4, which is how much is remaining after the 3rd halving. We go backwards another one, okay, we go 4.8. We go again, okay, and you take your 4.8 and you times it by 2, and you get 9.6, and you take your 9.6 and you times it by 2, and you get your 19.2. Notice why the 0 line is really helpful. A lot of people would have doubled back up and they would have stopped here after the first halving. No, you want to find the original amount when there was no halvings, when there was no time, when you had 100% of the sample. Okay, so that's a really good half-life problem that shows you how much of the original sample you had to double back up. Now, a lot of times the questions are done the other way. Hey, I had 19.2 grams of cobalt-60. After 21.84 years, how much is remaining? You would look up the half-life, divide it to find that it was 4, 1, 2, 3, 4, and what would you do? You would have 4 times. Okay, so let's put our 19.2 grams in our reference table. Or I should say, put it in our answer booklet, because the answer to the reference table is not a place you put your answers. Haha. And they're not looking for sig figs, so 19.2, 19.20, that really works. They probably would accept 19. Okay, they didn't ask you to answer to a particular decimal place. All right, significant figures were not asked. They don't need to be shown. So 59, 19.2, 19. Okay, all works there. On to 60. Okay, number 60. Determine the number of minutes that the substance was in the liquid phase only. So we're going to look at the cooling curve. So we definitely have to look at the information above. A lot of times these questions have very little to do with the information above. People get intimidated, but here we need the cooling curve. We should not be intimidated by the cooling curve. Things or phases that exist at the highest temperature are gases. And I know that a gas, a pure phase, can have a temperature change, because I know that when there's a phase change, in this case it's a gas going to a liquid, there's no temperature change at a phase change, because kinetic energy, potential energy, okay, are being interconverted there. Okay, here is going to be the pure liquid phase. There's a pure temperature. Liquids can have a temperature change, but a phase change cannot. That's a liquid to solid, and this is a solid. And I know that solids have lower temperatures than gases, and liquids are in the middle. So the number of minutes that the substance was in liquid phase is from 6, from this point where it first starts to, when it's 100%, the first point where it's 100% liquid, okay, is right at C. So this liquid, it's 100% liquid where it first is, and all of a sudden it goes to D, and D is where it first starts to freeze. So between 6 and 11, this time period is where you have the liquid phase only, because in this area, B to C, you're going to have liquid and gas. We can sometimes call that equilibrium. Okay, same thing here, you have liquid and solid. So only liquid would be in this phase from C to D here. So we're looking for 6 to 11, and they want the number of minutes, 11 minus 6, and that is going to be 5. 5 plus 6 is 11. So 11 minus 6 is 5 minutes of just being in the liquid phase. Let's get that into the answer booklet. And so it is 5 minutes. You can put 5.0 if you want to be fancy. Notice they give you the unit, no sig figs, 5 minutes. And it's that simple. On to number 61. Number 61. Compare the strength of intermolecular forces within this substance at 180 to the strength of the intermolecular forces at 120. Okay, intermolecular forces, IMF, are the attractive forces between the molecules, okay, that keep them in the solid phase or determine if they're in the liquid phase or the gas phase. Now, at 180, okay, we have a what? A gas. And at 120, we have a liquid. So gases fly around the room hundreds of miles an hour, where liquids kind of stay in their container. So gases, okay, have weaker attractive forces. That's what makes them have a gas, right? They're able to move, so they overcome these things. So they have weaker attractive forces amongst themselves, okay, than a liquid. And that's really all you're doing. Gases, because they can fill their container and fly around the room, do so because they have weaker attractive forces. All right, so at that temperature, the attractions are weaker. For a liquid, at 120, they're stronger. And you may say, well, I'm kind of confused on that. Well, you'll learn that a positive attracting a negative electrostatic forces, which this is all about, has to do with distances. Because gases have so much kinetic energy, the distance between these molecules, if they're polar or non-polar, okay, doesn't really matter at this point. Their attractive forces are dependent upon distance. And the farther they are away, because of their higher kinetic energy, temperature is average kinetic energy, okay, the weaker this guy can have an attraction to this one. So the attractive forces really depend upon distance in this case, and at higher kinetic energies, they're farther apart. Okay, so it makes sense that gas is flying around because it has weaker attractive forces. So let's get this down to the answer booklet. So I said a gas has weaker intermolecular forces than the liquid. You could say this so many different ways. The liquid has stronger IMF than the gas. The intermolecular forces are stronger in lower temperature. The forces are stronger at 120. Okay, many ways to say this. On to number 62. Number 62, describe what happens to the potential energy and the average kinetic energy of the molecules of the sample during DE. So what we're talking about is we're talking about D to E, clear and simple. So let's make this line big, and we're going from D to E. Okay, now what is happening here? Well, we know it's a liquid going to a solid. That's the phase change. And we know the temperature is constant. Okay, now the average kinetic energy is temperature. So we know the average kinetic energy stays constant. Now, what happens to potential energy? That is not measured by a thermometer. Thermometers measure temperature or the average kinetic energy. So this is not measuring potential energy. So what I tell my students is follow the flow of the graph. This graph is generally going down. The energy is dropping because the temperature is dropping in the substance. Okay, it's dropping because energy is being released. All of these phase changes from gas to liquid, liquid to solid are exothermic. So the energy is being lowered in this system. I always say follow the flow of the graph. So if we have this gas becoming a liquid, eventually becomes a solid, a crystal pattern, if we follow this flow of energy as energy is released, okay, doesn't a solid have the potential to move less than a gas? Absolutely. As the temperature is dropped because energy is released during this entire process, the potential for these molecules to move drops. So I always tell my students, follow the flow of the graph. The graph totally from left to right really is going down. There are spots where it's not. But generally speaking, the energy is dropping in every single interval. Therefore, the potential energy is dropping in every single interval. Check it out. If you've got more liquid than solid at this point in right here, and at this point here, you have more solid than liquid. As you go across, eventually get to point D where it's 100% solid. So as liquid becomes solid, as you go from point D and move along this point here, more and more of your liquid becomes solid until it's 100% solid right here. So as you're developing more solid, you're developing more of these crystalline structures that can only what? Vibrate in their fixed positions in their crystal lattice. So the potential is dropping as you make molecules who have less freedom to move. If you don't like any of that, hey, the overall flow is going down. The potential energy drops for every single interval, okay? And that's important. So we say the potential energy drops while the average kinetic energy remains the same, right? The temperature is staying constant here, okay? Because of the conversion of potential to kinetic. All right, so let's go to the answer booklet. Potential energy decreases because energy is being released by the system. Okay, number 63. We have this little blurb here, and guess what? I'm not going to even read it. I'm going to go right to the question and see if I need it. I'm not going to be intimidated by any of this information that looks really weird. Okay, so let's go. Determine the number of moles. They want the number of moles of O2 in the cylinder. The gram formula mass of O2 is 32. That's kind of nice. Okay, so they want to convert the moles. Okay, and so I have to be given some value. So now I'm forced to look into the blurb. And what do they give me? Oh, there's 16 grams of oxygen. So they want the number of moles. So all I got to do is convert my grams to moles. So I always write down what's given to me, 16.0 grams. And how I remember this is I want to get rid of grams, so I put grams on the bottom. And I know that they're telling me the formula mass of O2 is 32 grams per mole. So there's 32 grams for every 1 mole. This is a converting factor, and I use dimensional analysis so that the grams cancel to give me moles. Now you can also think this through, because some people memorize when to divide or multiply. I like to use the units. Okay, so if I have 16, if there's 32 grams per mole and I have 16, don't I have half that? Sure. But if you don't like the math, just use your units. Get rid of the grams, the 32 grams per mole. I can write the grams and moles any way I like, but I write it so that the grams are on the bottom so I cancel. So in any case, it's 16 divided by 32, and that's going to be 0.5. And you're left with moles standing. That's all they wanted. They just wanted you to convert grams to moles, and they gave you 16, okay? And they gave you the gram formula mass of oxygen to be 32. They didn't even ask you to solve for that by adding the atomic mass of oxygen. If you look it up, it's 16, and because in O2 there's 2 of them, it's 2 times 16. They didn't even ask you to do that, okay? So let's get this down in our answer booklet. So our answer is 0.5, and whether you write 0.5 or you write 0.50 or add another 0 if you want to be fancy, it doesn't matter. They're not looking for the sig figs. Remember, ending zeros count, but 0.5 just works, or anything close to 0.5. Okay, so 63 is 0.5, on to 64. I think you can handle this question. On to 64. So in number 64, state the changes of both pressure and temperature. You better mention both, okay, of the gas in the cylinder. And of course, the gas in the cylinder, if we go back to the blurb, we're going to have to look into it there. Diagram below represents a cylinder with a movable piston containing the gas, O2. So we've got O2 in this cylinder, which means we have particles of O2, okay? And they're bouncing around and they're creating a pressure, which means a force as they smack into the container walls. And they want to know what would increase the frequency of collisions, what would increase the number of collisions, okay, between the O2 molecules inside. Well, I know for certain, okay, temperature is the what? Average kinetic energy. Boy, we got to get that down. Average kinetic energy is temperature, and kinetic energy is motion. So all we got to do is increase the temperature, and these guys would slam into each other more, and that would actually increase the internal pressure, and this syringe would move up. Okay, so definitely increasing the temperature. Okay, which changes its motion. Kinetic energy is motion. Now, what about the pressure? Okay, now in the cylinder. Now, how would I change the pressure? Now, pressure is the force over area. that is on the gas. People get confused. They say, well, wait, isn't there pressure inside? Yeah, but what's the pressure on them? So if I was to take this cylinder or this movable piston and push down, this would move down and I would actually make the space smaller. And if the space is smaller, the gas molecules have to be closer to each other and they will collide more often. So by pushing down, I'm going to add more pressure on them. So we're going to increase the pressure on them, force them to be closer together, and they would collide more often. Also increase the temperature, okay, which would also make them collide more often as they move faster. Those are the two factors that would increase the number of collisions inside this, make them go faster, and put them in a smaller space by increasing the force on them. Okay, so let's put that in the answer booklet. The change in pressure, you increase it, you can say higher, or you can say increase in temperature higher. Both have to increase or get bigger. You could also be more specific and say it's change in pressure. You could actually put down a pressure, any pressure greater than 0.5, and then any temperature greater than 298, which is the current um, temperature. So an increase in pressure, an increase in temperature. On to 65. Number 65 is the third final question on this gas law blurb of having a certain gas. Show a numerical setup. They just want a setup for calculating the volume of O2 inside the cylinder at a different temperature than what it was set up on and a different pressure. Okay, so we need our gas law formula. So let's go to table T. So here's table T in all of its glory. We're going to scroll down to combined gas law, and there we have PV over T equals PV over T. I'm not a big fan of the ones and twos. They get me crazy looking at them. This is the current condition, and I call this the future. Okay, so as long as you can put the pressure, volume, temperature conditions that go together for the current and then solve for the new, you're good. The twos and the ones drive me batty. But hey, let's continue on. Let's go back to the question and solve for it. All right, so I have my formula. I took out the ones and two. This is the current scenario. Let's go find the current values. Okay, and so currently I've got 298 Kelvin temperature. Remember that 298, your temperatures must always be Kelvin, so they gave us Kelvin. Great. We have a pressure of 0.5. Okay, I'm just going to put that in. And we've got a volume in my syringe to be 24, that's a big syringe, a movable piston, 24.5 liters. Okay, those are my current conditions, my pressure, my volume, and my temperature. Okay, what's the future? Okay, in the future, we're solving for what? Hey, calculate the volume. So we're solving for V. Okay, what's the new pressure? Well, the new pressure is now 1 atmosphere. So I'm going to put that right there for P, 1 atmosphere. And it's 265 Kelvin. Okay, boy, you are done. That would be the setup. Okay, yes, to actually solve, you can cross multiply your hearts away, but that is a perfectly good setup, just plugging in. You put the current conditions together and you put the new conditions. That's all they want you to do. Let's put this in our answer booklet. And there it is. Now I put in the units. Sometimes it's good to put the units in just to keep yourself organized to know what unit you put where, but you don't have to put them there. You don't have to have a certain number of sig figs. They don't care. Just put the numbers in. So I didn't even solve for V. Now, of course, I could solve for V and put this value on the denominator and this on top, but that's all you need. That's all they require. Okay. So you could clean this up and simplify. You can do that if you like, but this is all they require. Okay, no units are necessary. Significant figures are not necessary. I think we can do this, right? Okay, on to 66. Okay, so we're into number 66 now, and we have this blurb. We have all kinds of information here that looks very, very strange. Okay, so again, I tell my students, go read the question first and then see how we can possibly use the blurb. Sometimes you really don't need it. You can cut through all of this information by knowing exactly what you need to solve for. So identify the phase of EA, and that is this predicted element that's kind of like aluminum at 310. So we want to know what its phase at 310 Kelvin is. So we look at EA, and what information do I have? It's got a low melting point, and its melting point is 30 degrees Celsius. If I look at densities, melting, molar mass, it's all I have is the melting point at 30 degrees Celsius. And they said, what's the phase at 310 Kelvin? Well, we don't want to compare two different temperatures at two different units. So we're going to basically convert Celsius into Kelvin to see what this looks like. And we have a formula in table T. Table T is where you look for formulas if you need one to do that. We want to convert the Celsius for me into Kelvin and compare the Kelvin. That's how I'm going to do it. So let's go to table T. So I go to table T and I scroll down and I look for my temperature formula, and there it is. Kelvin equals Celsius plus 273. So I'm going to use that to convert 30 degrees Celsius into kelvins. So there is my formula I got from table T. And let's solve for Kelvin. Let's convert 30 degrees Celsius into Kelvin. So it's basically 30 plus 273. And when you add this together, and you don't have to do it by hand, but if you have to, you can. This is going to give me 303 kelvins. So the melting point is equal to 303 kelvins. This is the temperature where a solid becomes a liquid. Any temperature above this, you have the liquid phase. Any temperature below this temperature, you've got the solid phase. And they want to know the phase at 310. 310 is greater than its melting point. So if you can't still see it, draw yourself a little, what? Heating curve. This temperature right here is 303, where the solid becomes a liquid. And anything above that temperature is a liquid. And guess what? 310 is above that, so you have the liquid phase. So we write liquid phase. So essentially, this question was about just converting your Celsius into Kelvin and then seeing if the current temperature is above its melting point to notice it was a liquid. That's it. All the rest of this stuff was not needed. I think it's very doable. Don't get intimidated by all this information. Let's get that down in the answer booklet. So I write liquid. That's it. Number 66. On to 67. Okay, number 67, write the chemical formula for the compound between EA and Cl. So EA is this predicted element that Dmitry Mendeleev from the thought was like aluminum. Okay, so we have to go back into the blurb. It may help us. Dmitry Mendeleev developed a periodic table of the elements known at the time. Based on the pattern, he was able to predict properties of some elements that had yet to be discovered. And what we find out is that he put elements in what? Groups, which is columns, based upon their similar chemical properties. So carbon and silicon went under each other because they behaved chemically. We now know why. They have similar valence electrons. Okay, so he called this EA, or Eka aluminum, because it had the similar properties of aluminum. And therefore it has, guess what, the same valence electrons. So if we go to the periodic table, we'll find that aluminum has 3 valence electrons, and because it's a metal, it becomes +3. And we could build the formula they're asking for 67 based on that. If we go to the periodic table, we can see where aluminum is and see that it would become +3. So anything that's aluminum has the same chemical properties, has 3 valence electrons. Now Dmitry Mendeleev didn't know that back then. They didn't discover electrons too much later, right? That's the J.J. Thomson cathode ray experiment. So Dmitry Mendeleev was way before that. He just knew that boron, aluminum, or anything that's like aluminum behaves similarly. Now we now know it's because they all have 3 valence electrons, which means they like to lose them because they're essentially okay, very much like metals. And most of them are metals. They're +3. So anything like aluminum would be +3 when it binds to things that are negative. Notice oxygen is -2, okay? Okay, so that's important in that question where we're trying to write a chemical formula of this compound or this element called Ea, which is a lot like aluminum. It has the same chemical properties. That's how we could attack it. Now, of course, chlorine, which is essentially, okay, over here on the periodic table, let's move to chlorine. We see chlorine right here can be -1. So if an element that's in this column, which is what was built with Dmitry Mendeleev, is +3, okay, and chlorine is -1, you know when you make a compound, you have to do what? Have a neutral compound. So you would need, if you crisscross, you need 1 Ea, right? And then 3 chlorines, and that'd be EaCl3, and that's one way you could do this. You can also do this another way. Let's go back to the answer booklet. All right, let's go back to the question. Since the question in 67 is about writing a chemical formula, and we know the oxide formula, we could figure out the charge of Ea. So this is another way to do it, and I'm just going to give you both ways. Okay, and what do we know? Just from the periodic table, oxygen likes to become -2, so I like to write the individual charge on top. All right, now the bottom is the overall charge. Now, because there's 3 of them, 3 times -2 is -6 overall. Now, the Ea has to be the positive part because this compound does not have an overall charge, so it must equal 0. So what number plus -6 is 0? Obviously, it's +6. Now, what makes +6? 2 Eas. So the individual Ea is +3. And knowing Ea is +3, and knowing that a halogen like chlorine is -1, okay, you clearly, if you want to crisscross, okay, or you want to just figure out that you need what? 3 chlorines, which are equally -1 apiece to give you an overall -3, will match and neutralize, or at least match the +3 to make the compound 0. So that is your formula. I don't care which method by which you went about it, but it wasn't that difficult. The key was looking at either this hint or understanding this was a lot like aluminum, who was +3 because of its 3 valence electrons. Either way, not very difficult, okay? And I know you can get intimidated with all this information. Most of this you don't need, so read the question first. Let's get this down into the answer booklet. Now, I put EaCl3. Now, some people actually put Ga, gallium Cl3. Gallium's in the same row, okay? And if you were to look up the information that they've given, this information that's listed in table S actually matches gallium. So you can put gallium, okay, there. And we probably would accept if you put any element, okay, that was in the row of aluminum in this place. But essentially, it's one of these to 3 of these. So the actual element that they were describing was gallium based upon the information that was given for them in table that they gave you in the question. So some people looked at this density 5.9, okay, melting point of 3 Kelvin if you add 273 to it, okay, and even the molar mass, and you looked under aluminum in the periodic table, the next element is gallium, and you could have found that element if you go to table S, okay, here we go, and we go down to atomic number 31, which is gallium. Okay, you can see there's atomic number 30 for gallium. You could see the 303 for the melting point, or the density matches gallium. So you could have put gallium there if you like. Okay, you didn't have to, but some people were showing off. All right, on to the next question. Okay, so number 68, they want you now to identify the element that Mendeleev called eka-silicon. So based on what we've done, if you've been with me, this blurb was about the fact that Dmitry Mendeleev put elements, he was able to predict properties of elements because he put them under each other. So silicon's like carbon because it has the same number of valence electrons. He didn't know about electrons, he just knew how they bonded. So we're looking for something that's like silicon, so it's going to be in the same column as silicon, okay? And all you really got to do is match the molar mass. Or if you go to table S, you can match the density. If you convert this to Kelvin temperature and add 273, you can match its melting point in table S. So what is under silicon that has the same molar mass, which by the way is the what? Atomic mass. Let's go to the periodic table. So something like silicon would be underneath it, and they're looking for something around 72. And look at that, there it is. So we think it's germanium. If we're not sure, atomic number 32, let's see if its density matches. Okay, so atomic number 32, let's go to table S. So 32 is germanium, and that's under silicon. And its density is 5.3234. And its melting point, okay, just make sure as we scroll up, okay, that's the density, and its boiling point, its melting point is down here. So its melting point is 1211, and of course that's in Kelvin. Let's see if that matches up in our table information in the questions. Go back to the question. And so if it's germanium, which we think it is, because it matches the what? The molecular mass or the atomic mass, and it's under silicon, so it's similar, bonds the same way. This is the same density that we just saw, and its melting point, if we add 273 to that, becomes 1211 kelvins, just as the same numbers for germanium. So 68 is germanium. Let's get that in the answer booklet. So it's germanium. You can write the symbol or its name. There it is, number 68. On to number 69. 69. Show a numerical setup for calculating the percent error of Mendelev's predicted density of ES. So if you notice, in this chart, we have to go into the chart. There's the predicted value, and there's the actual value. And of course, the actual value is what we call the theoretical value. Okay, so we want to make a percent error. So we need a formula from table T. Let's go get it. And so here we are in table T, and here is our percent error formula. Measured value minus the accepted, sometimes you can call this the theoretical, divided by the accepted times 100. Okay, it's a measure of accuracy. Let's go to our problem. So in 69, we're continuing on. They wanted a numerical setup for calculating percent error. And so we have our formula here from table T. And remember, it's for ES. Read carefully. All right. And so the predicted value, and that's, of course, the predicted value is the value that Mendeleev, came up with. That's his experimental or measured value. And of course, the actual value is what? What we are accepting as the known. Okay, so we put that in. So the predicted is going to be our measured, and it's going to be 5.5 minus 5.3, 234 divide by 5.3234 times 100. And that's all you need. Let's put this down in the answer booklet. Remember, anything we do on the test is not going to be graded. And there we are for 69. And there's our setup. We don't need to write the percent error, but this is essentially right here, what you have to write. So it's pretty straightforward. You don't have to put the units in. You can make this very more simplistic if you want. Some people will take these two numbers and subtract them, and you get something like 0.2, and then you can divide that by 5.3. Yeah, they're going to be rounding off here, and times by 100. They're accepting something along this line as well. So they will take the rounded versions. They're pretty much going to take anything that sets up the fact that you take the number that Mendeleev came up with as it's measured and accepted. So a lot of flexibility in how they accept this answer. You don't have to write the units. On to number 70. Number 70. There's of course a blurb, okay, that is written for you. But oftentimes, as I said before, people get intimidated by the blurb, okay? So let's go right to the question and see if we even need that information. State the class of organic compounds, okay? The class of organic compounds to which the product of the forward reaction belongs. So the forward reaction is this way, and they're doing that and saying that because it's an equilibrium. It has an ability to go in the reverse. So these are the reactants, these are the products of the forward, and since we're talking about the product of the forward, they are talking about that chemical right there. And they want to know what that is. Okay, class of organic compounds. You can't say organic. So where do we look for? So we needed to go back into the blurb, so to speak. None of these written parts are important, but what is that chemical? I see carbons and hydrocarbons, and I see some kind of structure. So I'm looking for what kind of functional group this OH is and what kind of organic compound has this functional group. Now, real quickly, if I have hydrocarbons, carbons and hydrogens, this part of the carbon and hydrogens represents the rest of the organic compound. Remember, carbon makes it organic. And then we have this what? We have this OH ending that comes off of it. This is not, okay, a base. It's not a hydroxide. It's covalently bonded. And so what is this? Where you have the R, the rest of the organic compound, the OH. If you don't recognize this, we go to table R. Let's do that. And so here we are in table R. And I hope you are getting most of what I'm talking about. Sorry. All right. So in any case, we look for our organic functional groups. Functional groups are a type of an arrangements of oxygens, nitrogens, mostly oxygens and carbons, but oxygens and nitrogens and how they bond with carbon in a certain structure that give the class. Remember, we were looking for the class of the organic what? Compound. So you can see how table R is definitely what we're after. And having a different arrangement of, let's say, hydrogens and oxygens and carbons and some nitrogen sometimes, we have a different type of class of compound that has unique properties based on this what? Structure. Structure gives function. Okay? Structure is king. So back to the problem. We're looking for the rest of an organic compound. Hello. And then of course we have this what? OH ending. It's called a hydroxyl. It's not a hydroxide. It's not a base. It's an alcohol. We're identifying an OH covalently bonded to some carbon chain. In fact, if you remember earlier in this same part 2, we used table R to name 2-butanol. Okay, so we had to go to table R to get what the OL ending was, and it was an alcohol. So this is not our first time using alcohol in this test. Interesting enough, they used alcohol again. So this is an alcohol if you have a OH covalently bonded, okay, to some carbon or hydrocarbon chain. So alcohol is what we're writing in our answer booklet. Let's go there. And here we are writing alcohol in our answer booklet for number 70. On to number 71. Number 71. And again, people sometimes don't like this little blurb and they say, oh, what is this stuff about? Go to the question first. Oftentimes you don't even need anything in this blurb. Now this is a small little blurb, but sometimes they get pretty crazy. Go to the question first. So here we go. Compare the rate of the forward reaction to the rate of reverse reaction in this equilibrium system. Hey, I've seen this question before, and this is a point I want to make over and over again. People think the part 2 is something totally different than the multiple choice. People say, oh, I can do the multiple choice, but the part 2 I just can't get, or it's really hard. The part 2 is the same curriculum as the multiple choice. If you were to work through the multiple choice questions 1 through 50, and you do a bunch of tests, you are covering the same curriculum that the part 2 where the free response actually goes over. And if you do enough tests, you'll see that this question comes up as a multiple choice question over and over again. Okay, so it would give you an equilibrium reaction, say which of the following is correct, or which of the following represents the equation above. And if this is at equilibrium, we say that the rate of the forward reaction equals the rate of the reverse. So they want you to compare the rate of the forward reaction, the rate of the forward and the rate of the reverse reaction, and they are equal. Now, people get this wrong. Okay, there's two parts of this, and I want you to understand this. Let's take another way to do this. Let's say you've got 10 people on a line. And I know people say, well, I knew the answer is the rate of the forward, but some people are going to say that, sometimes they say that there's something equal and something's constant. Just stay with me. There's 10 people on one line and there's 2 people on another line. And I'm going to make the people on these 2 lines, I'm going to make them switch lines at an equal rate. The rate of the forward equals the rate of the reverse. So I'm going to have one person go to this line at the same speed as one person goes to this line. And that's equilibrium. And so what you're going to find is, because the rate of people leaving this line to go this line is equal to the rate of these people leaving this line to go to this line, what's going to happen? Aren't we always going to have a constant 10 people and 2 people? Yeah, the people will change, okay? But what's going to happen is you're going to have the amount, or we say concentration, of the reactants and products, the amount is going to stay constant. That's important. And it stays constant because the rate of the forward equals the rate of the reverse. Okay, so it's important you get that, because that's going to be a multiple choice question. And if you were to do enough of these tests, you would have seen that this question pops up almost on every single test. Sometimes they'll go after, do you understand that the amount of reactants stay constant, like the people, or that the rate of the forward equals the rate of reverse, like this question. All right, so this is a gimme question if you see that this happens over and over again. All right, and if you think of it another way, if I have, water in a bottle, and this is my poor drawing of a bottle, and I close it, and I know there's a line of water, and I take my eyeball and I watch and I look, this line right here never changes, because the rate of what? Evaporation is equal to the rate of condensation. If I take open, or I open up that bottle, now the rate of evaporation is going to be faster, and condensation can't collect back, so of course the line's going to go down. All things you know in your surroundings. It's good, really very helpful to try to connect to the test. All right, let's get this down into the answer booklet. So I said the rate of the forward reaction is equal to the rate of the reverse. This is, again, much like a choice you'd see on a multiple choice question with the same concept. Guess what? The free response is the same type of concepts. They just do what? Try to hide them. Unpeel the onion and see it's the same. On to number 72. Number 72, explain in terms of collision theory. Please explain in the way that they want you to answer. Collision theory is the idea that molecules or atoms or ions must collide to form chemical bonds, okay? Or even pressure. There must be a collision that's effective. Okay, to be an effective collision, you have to have high enough kinetic energy. That's your activation energy. And the proper orientation, especially if it's a macromolecule where there's areas where things can bond and cannot bond. Any case, explain in terms of how atoms, molecules, and ions collide while increasing the concentration of H2. That means adding more of these guys, okay, will wind up, will increase the concentration of CHO3. So if increasing this, why does this go up? Now, in Le Chatelier's principle, we know that if I increase H2, the reaction is going to look to decrease it, so it would shift to the right. But Le Chatelier's principle works, okay, by decreasing H2 by going forward. Now, let me take a step back and describe that for a second, okay? Le Chatelier's principle is the idea that if you get a reaction at equilibrium, the reaction, okay, is going to jump out of equilibrium if you add a stress. Now, I teach it this way that I think is helpful. Here is the stress that we do, that's what humans do, and here is the response that the reaction does. And the response is it's shifting to the right. So they're not really talking about Le Chatelier's principle, but I want to talk about it because it will come up. And this is their way of kind of doing it. So what's the stress? There's an increase in H2. We've just unbalanced this process because you learn at equilibrium, the amount of reactants and products stay constant because the rate of the forward equals the rate of the reverse. That was we talked about in number 71. But if I increase H2, that's the stress. There's too much H2. So to rebalance itself, it's going to decrease H2. And how does it decrease H2? It's going to make the reaction go in the forward faster than the reverse. So there's a shift to the right. And so if you go forward faster than the reverse, hey, you're going to use up CO2. You're going to use up the extra H2 and you will make more. Okay? So that's kind of way to think about it. So the response is the reaction shifting. And why does it want to do that? Why does it do the opposite? Well, if I push on you one way, okay, won't you fall over unless you push back the opposite way? So a reaction wants to regain its balance. It always does the opposite. And its response is either to go faster to the right or faster to the left. That's what a shift is. Now, this reaction is not asking you to explain in terms of that, but you should know the shift means the reaction is going one way faster than the other. And the only way that happens is because these guys are colliding more often. So if you add more H2, H2 is going to collide more with the CO2, or in this case, I'm sorry, the CO, the carbon monoxide. Why? Because there's more of these molecules. Increasing the amount of H2 will increase the number of collisions with H2 to CO, and therefore it'll make the forward reaction go faster and produce more of the product. Let's get that to the paper, but always remember how to explain it in exactly the way you want to. I wanted to add Le Chatelier's in there because I don't know if this test has it, and that's kind of where it's popping up. And again, this could be in a multiple choice question. Let's get this to the answer booklet. So I said in 772, more H2 molecules collide with CO2 molecules producing more CH3. There are more collisions with the reactants. Therefore, you're going to make more products. Okay, on to number 73. Okay, number 73, state the effect on the rates of both the forward and reverse if no catalyst is used in the system. All right, so now I'm again, kind of confused about the catalyst in the system, so I'm going to have to go back. I know I keep telling you guys, read the question first, but they're talking about no catalyst was used. Therefore, there must have been a catalyst used. Let me go into the blurb and see what it says. Methanol can be, here we go. Methanol can be manufactured by a reaction that is reversible. In the reaction, carbon monoxide gas and hydrogen gas react using a catalyst. Okay, so this reaction to make methanol, which we found out in question 70, is an alcohol. Okay, all right. So what would be the effect of both the forward and reverse if there was no catalyst used in this reaction? Okay, so what does a catalyst do? We should know that a catalyst, okay, a catalyst is going to lower activation energy. So let me kind of make some room here to talk about that. And you should always think of catalyst, you always think of activation energies, alternative pathway. You should always think of the potential energy diagram. So I'm going to kind of do that here for you. So let's draw that, and I'm going to kind of white out some spots. It'll be a white, okay? So let's go here for a second. I'm going to white out some area, and let's kind of talk about this. So let's talk about a potential energy diagram. This is what you really need to have in your mind once you talk about you know, change of age, potential energies of the reactants and products, heat of reaction. All of this comes from the potential energy diagram. Now, this is potential energy. This is the energy that's in the what? The bonds of chemicals. And this energy is being released. It's after these arrows here. This is exothermic. If energy is being released, think about it, there must be more energy in the reactants than products. Remember, there's a pathway for the reaction to occur. And this pathway has what we call an activation energy that's required to overcome this little bump right here. Okay, this little bump prevents a reaction from going. Okay, so from here to the top of this bump here is what we call the activation energy. And by the way, this activation energy is the energy needed to for molecules to have, they have to have enough energy to collide effectively. It's the kinetic energy needed for them to overcome their repulsive forces. What repulsive forces they have? They have clouds of electrons, but you should know that's the activation energy. And the difference of where you start and where you finish, of course, right here, between these two lines right here, okay, and I'll draw that in brown because, I don't know, brown's not used. This is my delta H, and notice I started high and I went low, so it's negative. It's a negative value, okay? All right, so that's what exothermic have a negative delta H. Now, again, all right, this is the potential energy of the reactants. Hey, it's much higher than the potential energy of the products. There's a lot more energy in the bonds of the reactants. That's why they gave off any. Things that burn and explode are unstable and have higher energy. That's why we go from high to low. Now, what do we do when we add a catalyst? We make an alternative pathway. And that alternative pathway lowers this hump here, lowers this we call an activation barrier, a barrier for the reaction to go. This reaction will not occur unless you have exactly this activation energy. But my friends, if you add a catalyst, which creates another pathway, an alternative pathway, this activation energy has been lowered for the forward. But wait a minute, the reverse is a reversible reaction. We do also have activation energy to go in the reverse, which is of course higher in the endothermic pathway, is right here. To start here and go in the reverse, you got to get to the top of the hill. And I always tell my students, if you want to ride a slide, and who doesn't like slides, to ride the slide, you got to get to the top of the slide. You got to add energy. And that's what activation energy is. But the reverse is higher. However, guess what? If you add a catalyst, this hump is lowered. Okay? And therefore, the activation energy is lowered for the reverse as well. So because a catalyst lowers the activation energy for the forward, as much as it lowers it for the reverse, there is going to be no effect, okay? And this reaction, of course, it will stay at equilibrium. What it does do, though, is make the rate of the forward faster and the reverse just as fast, so you get to equilibrium faster, but you don't change equilibrium, and it's not going to have any effect, okay, on equilibrium, all right? So now, if, of course, if you add a catalyst, okay, it'll increase the rate of the forward and rate of reverse. Now, if you do what? Okay, if you have no catalyst, remember this reaction again was started with a catalyst. So if you have no catalyst, what's going to happen is, so if we get rid of our catalyst here, what we once had lower activation energies, now our activation energies are going to be higher for both the forward and the reverse. So this question is all about the fact of what is the effect of the rate? Well, catalysts make reactions go faster by lowering activation energy. So if we have no catalyst, okay, our activation energies for both the forward and the reverse will both increase the same amount, okay, and therefore they're both are going to get slower. Equilibrium will still be intact. And that's not what they're asking about, okay, but both rates will get slower. Okay, so let's get that down into the answer booklet. So I said the rate of the forward decreases, the rate of reverse decreases. Of course, you can say slower. You didn't have to say that it decreases the same amount as I talked about, but that's something you should be aware of, that a catalyst doesn't really change equilibrium. It'll make the reaction get there faster. Without a catalyst, it'll get there slower in this case, but they will have the same rate of the forward and rate of reverse because you're doing what? You're lowering the activation for the forward and reverse the same amount. So on to number 74. So number 74, again, they've got this blurb here. People get intimidated by the blurb in part 2. Oftentimes questions, you don't even need this. So I always say, read the question. So let's go there. Write the molecular formula. The molecular formula tells us, as a molecule, how many carbons, how many H's, how many nonmetals are involved. Notice I say nonmetals because a molecular substance is a substance that forms molecules, an exact number. And that does so because nonmetals are sharing electrons with other nonmetals so that each atom has a stable, okay, electron configuration by the sharing. Any case, then what the formula of this entire individual molecule, which is a fatty acid, an unsaturated fatty acid. Okay, so all we've got to do is essentially count. This is a question of counting. So usually in hydrocarbons, we go carbon first, then we have the hydrogens, and then we have the oxygens. Okay, so we're going to count. All right, so I'm going to cross. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it is C18. Right? It's not based on structure, it's just on the number of each different type of nonmetal in this molecule. Let's do the H's by a different 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So I've got H32, and by heck, another color. Let's count the oxygens. That's an easy one, and that's 2. So what I get here, okay, is I get essentially C18, H32, O2, and let's put that down in the answer booklet. So there we are, question 74, just writing down the actual number of the individual nonmetals in this molecular or covalent substance. And by the way, even though with organic compounds we do carbons, hydrogens, oxygens like this way, you could have written this as O's or H's. So the order of the elements did not matter, just exactly how many, and all you did was count. Yeah, so this part 2 is so hard, right? All you had to do was count. I know there's concepts behind that, but you can't be intimidated by the free response, as I know some are. On to number 75. So number 75, identify the type of chemical bond between the oxygen atom and the hydrogen atom in this acid molecule, fatty acid. So between a carbon and hydrogen, okay, we've got two nonmetals, and you should know nonmetal and nonmetal is going to be a covalent compound. So nonmetal and nonmetal, okay, I can write this, is definitely covalent. Now the reasoning behind that, and that's important, is that nonmetals on the periodic table are up to the right on the periodic table. They're the smallest atoms. They're the smallest atoms because they attract their electrons so much they pull them in. They have a high nuclear charge, which means they have a lot of protons in their row. And because they have a high number of protons in their energy level, they pull in electrons in very close. And we say they have high electronegativity. It's a word you need to know. Okay, it's listed in table S. So when nonmetals like carbon and hydrogen form a bond, okay, carbon has one valence electron, carbon would have four, obviously, but between the carbon and hydrogen, one electron of its valence is going to have to be shared with the valence of hydrogen. And when that happens, we say that this carbon is sharing 2, and this H feels like it's sharing 2. Now the reason they have to share is the electronegativities of both of these are very high. Carbon is 2.6 and hydrogen is 2.2 if you look that up in table S. And that's of course the electronegativities. And electronegativities are like the strength for electrons. They're the attraction. And notice I put this pair closer to the carbon. This is showing that carbon is pulling this pair closer because it has a higher electronegativity, okay? And because they both are high, because they're both nonmetals, that's really a property of a nonmetal, is their high attraction for electrons. None of them is strong enough to yank them away. Here we're showing sharing unequally. By the way, we would call this a polar bond. In New York State, we call it polar bond between the carbon and hydrogen because electronegativities are different. But in any case, more importantly, is that they're forced to share. Okay, so you need to understand and represent yourself well by knowing that this is a sharing bond. And by sharing, hydrogen, who normally has one electron, okay, as an atom, now feels like it has two, and because two electrons fill the first energy level, by sharing two, it feels like it has a full complement of electrons, and its first energy level is now stable. Carbon, of course, makes four bonds because it'll share more electrons in with three other atoms, and that's why it makes four bonds. So in any case, all they want you to recognize that this was a covalent bond. By the way, molecular compounds are things that have covalent bonds in them, and you should know who your nonmetals are. They're above the staircase. So in your periodic table, okay, I like to take this table, when I look at it, I just say, okay, right down the line here, and these two, these are my metalloids, and everything above the metalloid here is our non-metals. H is written way over, okay, this way, but it belongs with the nonmetals. They all have high electronegativity in this area, and therefore when they bond with themselves, they're forced to share. And you should recognize, if I take a nonmetal, okay, like oxygen, and I bond it with a metal who's to the left, okay, any of these metals here, that's going to be a ionic bond. Why? Because this guy is going to lose electrons to the what? To the nonmetals. Why? Because they have a high attraction, and metals by definition have low. That's why metals oxidize. Leo, the lion, says grr. Got to recognize covalent within the same nonmetals, forced to share because electronegativity difference is similar. Like me and my brother pulling electrons, okay, have the same similar strength, so no one's strong enough to yank the rope away. But this would be like me and my third grader. I can yank the rope away. I'm stronger, and therefore I'd become negative, and this would become positive, okay, and we'd stick together by differences of charges. We'd make ions. All right, so let's write the chemical bond covalent, okay, in our answer booklet. So I write covalent bond, but what's nice about part 2 is it's open for interpretation for other things that are right. So it's a covalent bond, and between the carbon and the hydrogen in New York State, we call this a polar bond. So you could have said polar bond, you could have said polar covalent bond. Okay. Also, this is a overlap of orbitals. You could say it's a sigma bond. So there's all those possibilities you have in the part 2, and that's why people actually start liking the part 2, because there's more than just one answer or one choice like you would have in a multiple choice. Okay. Also understand that I like to think of covalencing. Remember, we talked about hydrogen has one valence, carbon has four. So by sharing, they're covalencing their what? Outermost electrons, so they can both achieve stable configuration. Another way to think about covalent bond. Any case, on to number 76. Number 76, on your diagram in your answer booklet, circle the organic functional group. This is the arrangement of a certain type of carbon, hydrogen, nitrogen, or oxygen on a hydrocarbon chain that gives its functionality. Okay, very important. You change the structure, you change its function. So the types and class of compounds that we have in table R, okay, help us identify the different types of organic compounds that are similar based on similar what? Structures that give them similar function. Structure is king. Let's go on to number 76 in the answer booklet, and let's look for, okay, that functional group. So in our booklet, we have a functional group. So looking for the arrangement of carbons, oxygen, hydrogens that give this molecule unique properties. Some people think it's the bonds between the carbons, and this gives it that ene. This gives it, makes it unsaturated. Okay, but and I know it changed its structure a little bit. It definitely has some effect, and it would change its name. But a functional group is a different type of arrangement on a hydrocarbon chain. Okay, and this is what we'd have to circle, because this is what makes this class of compounds an organic acid. That little arrangement at the end. And if you think with me for a second, okay, this right here is the organic hydrocarbon chain. We often, in table R, which is where they list the functional groups, will write R. And I always like to say that means the rest, okay, of the hydrocarbon. So we have R, and in this case, we're going to have a carbon double bonding to an O, single bonding to an O into an H, and we call this little structure with the R and that functional group, okay, on table R, a formula to figure this out. So let's go to table R to show you that. So here are our functional groups, table R in all of its glory, and we go down and we're looking for these general formulas. And notice the R, okay? The R is the rest of an organic chain. Okay, if you look and scroll down, where do we have an organic chain, hydrocarbon chain, and then we have this new structure right here, and this carbon double bonded to an O to an OH is an organic acid. They didn't ask for it by name, but they could have. They just wanted you to circle that structure, and there it is. Okay, and here's the rest of the organic chain is there. So all you had to circle was one of these functional groups. Okay, they're not always going to be at the end. The ketone is in the middle. Notice the general formula R. Hey, it's the rest of some hydrocarbon chain. R prime, the rest of another organic. And look what's in the middle, a carbon double bonding to an O. So that's how you use those general formulas if you haven't figured that already. Okay, so back to the booklet. So there's my circle, although they did say draw and circle it, so I would actually lose points because it's not a perfect circle. Just kidding, you don't need a perfect circle. Now, whether you circled outside or on or out of this bond, it doesn't matter where your circle is as long as you're going to you know, encircle the COOH here, where this line, whether you have it over here or in front, doesn't matter, okay? So just make sure you have that circle there, and if it's not a perfect circle, that's okay too, but that's your functional group, and table R shows you the different types of structures. On to number 77. So in 77, we've got this new blurb of information with a crazy diagram, but I do see a voltmeter. Ooh, and I see that, okay, with voltaic cells, but it doesn't really matter. Don't even read it. Some people look at this and say, oh my God, I could never answer this question. I have no idea what this diagram is. Who cares? Go to the question first for number 77. Let's see if it has anything to do with that, because oftentimes it doesn't. Do not be intimidated by the blurb. Attack the blurb. Say, no, I'm not scared of you, blurb. So number 77. What do they want you to do? Oh, it's kind of scary, these questions, because I have this information here that I know nothing about. Balance the equation in your answer booklet. What? That's all they want. Some people leave this stuff blank because they don't know what to do. Oh my God, I'm so scared. They just want you to balance the equation. That's it. And of course, listen carefully, or listen to yourself if you read it in your head, using the smallest whole number coefficients. So let's go to the booklet and just balance an equation, and that's a skill that pops up in the part 2 a lot. So let's go there. Let's continue on this scary question, okay, which is just balancing. And of course, when you balance, you're balancing mass and charge. This is no half reactions here, so you have to worry about redox reactions, but we're going to count the number of individual types of atoms, make sure they're equal on both sides, because we do have a law of conservation of mass here. Mass and charge and energy is always conserved, but here we're really after balancing these coefficients in front. So we have two H's. Hey, I have two H's. So far, so good. Two hydrogens on the reactant side. Remember, the reactant side's in front of the arrow. And we have what? On the product side, we've got two H's. Okay, so far so good. We have two oxygen atoms on the left hand, and then we have one. That's a problem. It's not balanced. So I've got to put a 2 here, and 2 times the 1 gives me 2 oxygens, and that balances fine. But what it does is unbalances my H's, because 2 times that's little 2, okay, is going to give me 4 H's on this side. But this side only has 2 H's, so I put a 2 in front. Okay, now there's nothing in front which implies a 1. You can write that there or not. And that's essentially all you're doing. So from that very, very difficult question, all we're doing is balancing Okay, this right here. So it's a 2, 1, 2. I'm not sure why that moved a little bit, so I'll rewrite it. So this is 2, 1, 2. And 2 times 2 is 4 H's. Hey, 4 H's on this side, hydrogens. This is going to be um, 2 oxygens on this side with the one in front, and this has 2 oxygens here because each O, there's only one of them per one molecule. So all you've got there is 2, 1, 2. You can either have the coefficient here or not. It does not matter. Leaving it blank is the same thing as 1. If you were to balance this and you had 4, okay, 2 and 4, for whatever reason, balancing is like a puzzle. Sometimes we attack it differently, but you had 4, 2, 4. I'd have to mark that wrong because they asked to what? Reduce it into the lowest whole number ratios. And 4, 2, 4 is not. Okay, so just be wary of that. Okay. So that's all they wanted for number 77 of this crazy, okay, very scary blurb they gave you that came with these questions. You didn't even need it. Don't be intimidated. Go to the questions first. On to number 78. Number 78, determine the change in oxidation number. That means this is a redox reaction for oxygen. Now, when they say oxygen, they mean O2. Anytime you say an element that's diatomic, it's O2. It has a 2 in front of it. To remember your diatomic elements, I have what I call the Hofbrinkels. Some people call them Brinkelhofs, but it doesn't really matter. It's a mnemonic that helps us remember those elements. Then when they're hanging out by themselves, are bonded to themselves. Okay, they're all diatomic. All right, so we want to determine the change in oxidation numbers in the operating fuel cell. Now, they gave us an equation, so we don't have to look at this diagram at all, but go right to the equation. And I know something. I say atom, you say what? You should say neutral. If you've been through me enough times, atoms are neutral. And why they're neutral? Because the protons, which are positive, okay, are equal to the number of electrons, who are negative. They're the same size, magnitude of charge, but opposite in sign. So this gets a 0. It's an atom. Now the question is, what's the charge in oxygen? Okay, well, each hydrogen is +1, but we know that oxygen is almost always -2. Just to check for that, it's -2 overall because there's only one. This must be +2 overall because water is a molecule that has no overall charge. It must equal 0. And because there's two H's, each H is +1. And that works out for me because hydrogens, if you look it up on the reference table, can become +1 or -1. And that's a good way to check. So oxygen almost always is -2. There is some small exceptions to this when it's a peroxide or hooked up with fluorine, but you can figure it out by the same method. Does the other one make sense for it? So oxygen is -2. So all you got to write is that we're going to go from a 0 to a -2. And how'd that happen? Oxygen was what? Gaining electrons. That's what nonmetals do. It's an oxidizing agent. It helps pull electrons away. So let's get this down into the answer booklet. That's all it was asking you to assign oxidation numbers. And we're going to go from O to -2. All right, on to the booklet. So we go from O to -2. Okay, that's all she wants there. Again, not a very difficult question. It was assigning oxidation numbers, and you should recognize that atoms are neutral and get a 0. Standalone atoms are always 0. So not a very difficult bunch of questions here for a crazy setup that some people are intimidated with. On to number 79. Number 79, state the number of moles of electrons that are gained when 5 moles of electrons are lost in this reaction. Okay, well, I'm laughing because I've seen this question so many times and I've seen it in the multiple choice section so many times. So if I write redox, what do we know? Well, oxidation is Leo. Losing electrons is oxidation. So this guy is going to lose electrons. And I'll write the E negative. Now, it just doesn't lose them. Someone needs to gain them. And these electrons are gained by the half of the reaction that reduces. And that's the GER part. Gaining electrons is reduction. So electrons go from oxidation to reduction, losing to gaining. And by the way, we have something called conservation of charge. The amount of electrons that are lost have to equal the ones that are gained. Because if that's not the case, we are going to create or destroy electrons in these chemical reactions, and that's not what we're doing. We're just throwing around the same. So as we've seen, if you've been with me with other questions or doing your own work in multiple choice questions, they will have a question that says, hey, how many electrons, okay, are gained if 5 moles electrons are lost? And they'll have different choices, and the answer will be 5. It's the same number. Some people left this blank in this actual test last year. They looked at this and say, I have no idea what all this means. I can't answer this question. The number of electrons lost is equal to the number of electrons gained. Why? Because if you remember half reactions, in a half reaction, it's the same electrons on both sides. Okay? Always when we do half reactions, we have the same number of electrons on the product side as the reactant sides. And if you don't, if you remember, we times it by 2 or some factor so the electrons can cancel in the overall reaction. The same number of electrons lost have to be the same that are gained. Okay, always. So therefore, it's just that simple. You would say 5 moles, and everyone thinks there's some crazy calculation here. No. And if you do enough tests, you could identify that, and that's what's so important. To number one, do enough tests and realize if you go through multiple choice 1 through 50 enough times, you will be working on the same material that you will see in part 2. It's just they choose sometimes to put this in a multiple choice, sometimes in a part 2. If you start seeing this, now you're ready for the test. If not, you need to do more questions. Okay, so let's get to the answer booklet. So whether you write 5 or 5.0, it doesn't matter. The significant figures don't matter here. It's just 5. 79 is 5. On to number 80. Okay, so number 80, state the number of significant figures used to express the concentration of Z. So now I got to go back into this blurb and look at Z, and now I have to know my laws of significant figures. This is the only question on this test that cares about significant figures, and you never had to round to any of them correctly for any one of these math questions. So given this number, how many are significant? Okay, party people, look at our rules. First rule for significant figures is all non-zero numbers, all non-zero, are significant. And that just means that that non-zero number came from a measurement device. If the number came from a measurement device, it's significant. So all non-zero numbers. So we start with, hey, there's my non-zero number, 1. So I know I definitely have 1, and it's going to get confusing if I try to write on that. All right, cool beans. If beans are chilled. So I know I have at least 1 there for that integer. Now, number 2, which doesn't apply here, but sometimes it does, sandwich zeros. Now, what's a sandwich? 0. Zeros that are between non-zero numbers, like 101. This 0 is significant. Okay, so sandwich zeros are significant as well. Okay, what are else that are significant? Well, we have to deal with the zeros. And the last rule, but you can make it into 3 and 4, is anytime you've got zeros that are placeholders, trying to get you out to a small number or helping you get out to a big number, they're always non-significant. So this case, we're trying to get to a small number, so leading zeros are never significant. So leading zeros, which are placeholders, leading zeros are never significant. Never. It's a strong word, but hey, it's true. Never significant. They're helping us get to the number, okay, that came from the measurement device. Okay? And then number 4, which I'm running out of room for, I'll put it over here. It's also part of the what? It's also part of the placeholder. That ending zeros that you add to make the number bigger would not count. So ending zeros would be placeholders too if there's no decimal place. So ending zeros are only significant if a decimal point is present. Okay, only significant if the decimal is present. Okay, easy for me to say. Let's go through them. All non-zero numbers are significant. That's therefore the 1 counts. Sandwich zeros. We don't have any sandwich zeros, but if I had 0.00101, that would count along with the non-zero numbers because it's sandwiched between two non-zeros. Okay, leading zeros are never significant. That's why we cancel them out, because they're just placeholders to get us out to a small number. And that's why I get rid of those two. But ending zeros are significant only if the decimal point is present. Well, I know it's hard to see. So we would say there's a decimal point and it's present, so that ending zero was measured, it's significant. So leading zeros don't count, non-zero number counts, ending zero counts because the decimal point is present, and that's going to be two significant figures. Okay, so that's a little review of how to look at a number, a raw number, and see how many digits came from the measurement device, which is called significance. Okay, so number 80 is 2. Let's get that down in the answer booklet. And so I wrote 2. You can also write out the word 2. All right, so 2 significant digits. On to number 81. Number 81, determine the concentration. That's the molarity. Okay, because there it is in our table, of an HCl aqueous solution has a pH value of 4. Now, this is a skill you really should have learned in your Regents chemistry class. But if you didn't, you could use the trend. What's happening to the pH value as this number gets what? Smaller as the 1 moves to tens place. Okay? Now, if you put this in an exponent, this is 10 to the what? 0. That's what 1 is. This is 10 to the negative 1. This is 10 to the negative 2 with your exponent base 10. This is 10 to the negative 3. And these are what the concentrations are. And they're getting smaller of an acid, and the pH is increasing. As the amount of acid decreases, your pH value increases. Well, why? Well, party people, you should realize that the pH value, this little p means take the positive value of the H concentration. Because it's a strong acid, every single H comes off, so the concentration of the acid is the concentration of the H plus that comes off. Remember, H's in front are screaming they're acids. So if you take the positive value of that exponent, that's your pH. Positive value negative 1, hey, 1. Positive value of negative 2, 2. Positive value negative 3, 3. So if we want a what? A pH of 4. What do you think this is? 10 to the negative 4. And that would be good enough. You could say 1 times 10 to the negative 4. You could also write this as 0.0001. Okay? Or if you knew nothing, what little p means the positive value of the H, which, by the way, for a higher level chemistry class, it'd be the negative log. But you can just think of it. Look at the pattern. You can just say it's moving over 1, and you'd be able to figure that out. So the pH, of course, is increasing. And you should also know, even though this was not part of this question, that if I go from a pH of 1 to a pH of 4, isn't that an increase of 3 digits? It's also an increase of 3 exponents, and you would say that the basicity increased 1,000 times. 10 to the 3 is 10,000 times. Also, you could say if I went from a pH of 1 to 4, which is an increase of 3, 10 to the 3, that the acidity decreased 1,000 times. You'll see that, even though this question didn't present it that way, that's what they're kind of using. They were using this understanding that a pH value that we use to measure acidity or basicity, or acidity and alkalinity, that means the same thing, is based on a exponent scale, base 10. So every single integer movement is a individual 0 change. So if I went 1 to 2, the basicity increased 10 times. This would be 100 times. And there's my 1,000 times. Okay, so understand that. Any case, all I'm looking for is 10 to the negative 4, or this number here. Let's get that into the answer booklet. And there I have 10 to the negative 4, or I can just write it out 0.0001. It has to have 3 zeros, okay, in front. That's what 10 to the negative 4 means. Or 1 times 10 to the negative 4, it's the same thing. Okay, so on to 82. So number 82, determine the volume of a 0.25 molar NaOH. Hey, that's a base. That's a metal ion with a hydroxide, also listed for you in table L as a base. that exactly neutralize a certain volume of solution X, which we've learned is an acid with that H in front, which by the way is listed in table K. Okay, this is a classic math problem you see almost on every single Regents, whether it's in the multiple choice section, normally in the part B1 area, okay, from 31 to 50, or in this case, part B2 or C, okay, that asks you to calculate. So what we use in a neutralization, okay, question where I have acids and bases involved, we use the MV of the acid equals the MV of the base. And we call this type of problem where we use the information of one chemical, okay, to get information of another. We call that a titration. And in table T, they write this as a titration formula, okay? And another way to identify it too is that if you see big M and you see, okay, a volume, and you see another big M because they're talking about determine the volume of a base that would neutralize of solution X, okay, is right there. So they're giving me another molarity. So I have two big M's and a volume. How many factors are here? There's three. So to solve for it algebraically, you have to know 3 out of 4. Okay, but just real quick, so you recognize the fact that this is a neutralization question, and you've got to identify this question as MV. Let's go to the table T to see where this is if you forget. Here we are, table T in all of its glory. Scrolling down, and we're going to see a titration, and there it is. Molarity of the H plus an acid, molarity of the what? Base. They use A's and BB, but there you go. There's your titration formula. Neutralization is the key. Let's plug this in and solve for it. All right, so they want to determine the volume of the base. Here's my base, so there's my X. Write that there. And they gave me the concentration of my base. Really important to put these values where they belong, 0.25. Going to solve for X is equal to what? They want to neutralize a certain amount of solution X, which is an acid, H in front. So there's my 75. I don't have to convert this to liters because they're both in the same what? Unit, they would cancel. And then of course, the molarity, okay, of solution X is 0.1. That's the molarity of that acid. You had to be able to put that there. Okay, and now we're going to do our math. Okay, so we're going to do 0.1 times 75, and we get 7.5, and it's equal to 0.25x. All right, and so when we solve for it, we're going to put 7.5, okay, under 0.25, and that equals our x, which is our volume, and I get 30. And it'll be milliliters because we didn't change the unit, okay? All right, so 30 milliliters is my volume of my base. Let's put that down. They're not going to give you any credit for any work you do here, and they're just looking for the answer in the answer booklet, so let's go there. Okay, 82 is 30 milliliters, and certainly you could write it 30 point. Okay, they're not looking for significant figures in our rounding, so 30, 30 point, 30.0. Hey, we'll put 8 zeros, it won't matter. Okay, so 82 is 30, so on to 83. Okay, so I'm going right to the question. I'm not even looking at the blurb yet. I know that because they gave me some data, I probably got to look at it, but state the trend in the solubility of calcium carbonate as seawater becomes more acidic. Well, you have to know, party people, that as what? The pH gets smaller, we're getting more acidic, and you should remember that, right? If we're going to have more H pluses in solution, which really drives acidity, that means I'm going to have a greater number of them. For instance, if I have 1 times 10 to the negative 2 molar solution, now it's small, and I increase it 100, let's say 10 times, it becomes 1 times 10 to the what? Negative 1. And what is pH? It's the positive value of that exponent. So this is a pH of what? 2. And if this increases, this number here is bigger. Notice what's the pH? What's the positive value of that? It's a pH of 1. Therefore, as the number gets bigger, the exponent gets smaller. And so the acidic range, of course, is below 7. So here we are, people. And as we get more acidic, what happens to the solubility? This is a measure of solubility. This graph is going what? It's going up. So let's get down the trend. So as we get more acidic, we're able to dissolve more calcium carbonate. Unfortunately, calcium carbonate is a main component in seashells, coral reefs. So as we produce more CO2 in our environment, that CO2 gets absorbed by our oceans. Our oceans get more acidic, and we're actually starting to dissolve coral reefs and other types of marine aquatic animals that require the safety of this normally insoluble precipitate. So anyway, let's go to the answer booklet. Easy for me to say. So I said in 83, as the seawater gets more acidic, the solubility of the calcium carbonate, okay, which is like chalk, increases. Okay, that's all there is. Just reading the graph, but you had to know acidity as the pH is getting smaller. Okay, on to 84. Number 84, state the color of brome crescel green in a sample of seawater in which the calcium carbonate solubility is 10 to negative 2. So we go find 10 to negative 2, and we go find its solubility. And so there we're going to try to draw a straight line. Tough for me to do here. But looks to me, okay, that's a horribly drawn straight line, because it's really important to see that we are going straight down from this point, and I'm doing the best I can. The bottom line is I am below 7. Okay, 7 is right here, so I'm below neutral pH. I'm in an acidic range. So the question is, if I am in acidic range, more importantly, my pH is about what? If this is 7, this would be what? That's a terribly drawn. Maybe it's 6.5. The pH is about 6.5. Okay, looking at this point, I'm still drew it terribly. To me, it's about 6.5. It's about quarter of the way to the 8, and the 7 is halfway. So given that pH is 6.5, what's the color of brome crescel green? So I'm going to have to go to a table that tells me that, and that is table good, or table M. Let's go there. So table N lists the acid-base indicators, which are chemicals that change color in different pHs and help us determine the acidity or basicity, or help us in titrations when to stop adding acid or base when we get to neutralization. But in any case, in this question, we're in brome crescel green. And what do we know? How do you read this? Well, see these color changes? Anything that's 3.8 and lower is yellow. Everything that's 5.4 and greater is blue. Since we made the determination that my pH from the graph was below 7, okay, but definitely higher than 5, right? Right here, again, terribly drawn, but about 6.5. Then the pH is way above 5.4. So anything above 5.4 is going to give me a blue color. Then my solution should be blue. Okay, don't say it's green because brome crescel green is green. Okay, it's only green when it's in between this pH. So the answer here is blue because our 6.5 is above 5.4, and everything 5.4 and greater is blue for brome crescel green. So I write blue in the color blue. Not sure why they gave us so much space here. Okay. I guess if you write big, I'm not sure. All right, so 84 is blue. And hopefully you're not too blue, because we're on the last question here, on to number 85. Number 85, a sample of seawater has a pH of 8. Okay. Determine the new pH of the sample if the hydrogen ion concentration, that's H+. Hey, that comes from what? acids, giving them off, is increased by a factor of 100. So this is the question I was talking about in the previous part of this exam, okay? And I was talking about it popping up, and I was talking about it here, okay? So here was a question where it actually did come up. I didn't think it would. So going back to reality, up there goes gravity, and here we go. So we have a pH of 8. What does that mean? This little p, guys, means the positive value of the H plus ion concentration, base 10. So this means that the H plus ion concentration, the molarity, is equal to 1 times 10 to the negative 8 molar. So if I increase the acidity because I'm adding hydrogen ions 100 times, if this increases 100 times, isn't my new number going to be 1 times 10 to the negative 6? Oh, yes, that's bigger by 100 times. Put that in your calculator. And that's now going to equal the new H plus concentration. And of course, pH is the positive value of this H plus concentration. And what's the positive value of that? That is a 6. And that's the new answer, okay? Or that is the answer to 85. Remember, each individual movement in the pH scale is a 10 times change, okay, in acidity or basicity based on where you're going. Sorry for that pun. Since we're adding acid, okay, our pH was going to drop because the amount of H pluses increases. Okay, so an 8 to 6 is a 2 change, right? Hey, that's an exponent base 10 change. 10 to the 2 is 100. And that's how it all works. Okay, you see these questions, very classic question. I hope this helped. Okay, I will put in the answer booklet to close it out. So pH is 6. You can certainly write it out if you're like to. So a pH of 6, okay, is the answer, and I hope this was very helpful to you, and good luck in your endeavors, and especially on the Regents chemistry exam.